Welcome to another video. In this video I am going to solve a IMO problem, and this is from IMO 1993 and it is problem number 5, as you can see. Now this is another numerical functional equation kind of problem, and this is very classic problem for any contest. Here is the view of the problem. Let n be the set of all natural number. Determine if there exists a strictly increasing function from n to n with the following properties: that f of 1 equal to 2 and f of fn equal to fn plus n. Let's go ahead to the solution. Before seeing my solution, pause the video, give it a try. Now I guess you are done, so let's go ahead. Should make a claim as following: that f of fn equal to f of n plus 1, where f subscript n is nth Fibonacci number, as you can see. Now let's prove it using simple induction. Now it is not hard to see that our claim is true for n equal to 1 and 2 and for 3 as well, and I assume that it is true for n equal to k. So we can conclude that f of fk equal to f of fk plus 1, and that's why I can write the following thing as you can see in the screen. So using the property 2, I can write the following thing, and hence we have assumed that f of fk equal to fk plus 1. That's why I can write this. Another interesting thing to note is that the ratio of two consecutive Fibonacci number is going to converge in a special number that is known as golden ratio and symbolized by phi. Now see that for large n we can write the following thing. To see why the previous observation is true, you have to look into this thing, that f4 strictly lie between 5 and 8. That's why we can say that f4 can be either 6 or it can be 7. Now if you notice that box of 5 times 4 is equal to 6, so the difference is not large, and we can say that this is perfectly true for larger n. And from here I can say that if n kind of 5 times n plus k, where k is strictly between 0 and 1. Let's see the behavior of box of golden ratio times n and fn. Okay, so you can see a table here on where you can see that 5 times n and fn differs at exact 2 points, that n equal to 1 and 4. Yes, I am exactly talking about these values, and if you make the table large, you can see there are more n for which the values differs. Once again, you can see the table to make it sure that the number are different at n equal to 1 and n equal to 3. Now it's question, how can we fix it? We previously observed that fn can be written as 5 times n plus k, and its box where k is strictly less than 1 and greater than 0. So I think to make a table for k equal to 0.4, and eventually that works. You can see here the table carefully, that for the value, all value of from 1 to 4, this works. Now from here I got motive to prove that if x equal to 5x plus 5 times x plus 0.4 should works. So yeah, let's go. I should make a claim and try to prove that if n equal to box of 5 times n plus 0.4 should works. For this purpose, I should assume another new function that is defined by g from n to n, such that gn equal to box of 5 times n plus 0.4, and we have gn is increasing. Now in general you cannot see it's directly increasing, that's why I have to make it proof, and here is the proof. At first of all, notice that this following thing you can see in the screen is true. To see this, why this is true, there is a famous claim or famous formula in box function, that is box of x plus y is greater than or equal to box of x plus box of y for all real g. So g is increasing. Now we should try to find out the value of g of gn, and it can be described as you can see here. Now it's time to put the value of gn in the above equation to get the following thing. Now the main thing to notice that g of gn will be strictly less than the following value, because we know that box of x is strictly less than x if x is not integer. Now since 5 square minus 5 minus 1 equal to 0, that's why we can write the thing, and that's why I have use another inequality, that is box of x plus y less than equal to box of x plus box of y plus 1, to get this following stuff of things. From here I have make a pretty cool thing, that g of gn is strictly less than gn plus n plus 1. Now this is time to let's take off and finish this problem. To finish this problem we have to find the lower bound of g of gn, and in this purpose we have to use this inequality, and this is because box of x is always greater than x minus 1, and this is nothing new. So the above expression will be greater than equal to this thing, because of we use again this famous inequality, box of x plus y is greater than or equal to box of x plus box of y. So g of gn is greater than g of n plus n minus 1, and we previously get that gn is less than gn plus n plus 1, so only possibility is this, and we previously get that g1 equal to 1. So gn equal to fn can be a solution, and yes, there exists a function as defined in the problem. So we are done. For the PDF, please check the description out.